title might seem a little specific, so let me back up and say a few things about the topic. So what I'm going to be talking about is the interaction of supermassive black hole binaries at the centers of galactic nuclei with gas, specifically thin gas accretion disks. So of course, the in-spiral and merger of massive black hole binaries is one of the loudest sources of gravitational radiation in the universe and a primary source for detection in the future. And the merger events which create the binaries in galactic nuclei should also deliver gas to the vicinity of the binary. And so the interaction of this gas and the binary is interesting because it could cause accretion onto the binary. And if this accretion is vigorous enough and perhaps a variable, it could create unique signatures of the binary that we can detect electromagnetically, or in the future as a counterpart to gravitational waves. In addition to accretion, forces on the binary from the gas can also change the evolution of the binary in time. So for example, add to its change in separation and eccentricity, in addition to anything else like stellar scattering or gravitational wave radiation reaction. So then, what I want to talk about, and to understand whether the accretion signal will be interesting or if the orbital evolution from gas will be interesting, is study of fundamentally just the interaction of a hydrodynamic accretion flow and a binary. And so Zoltan is going to split this session with me and then also talk to you about how that applies to looking for binaries electromagnetically. But for now, I'm going to talk about some recent work that I've been doing with Zoltan and also our collaborators here, Paul Duffel, Brian Ferris, Andrew McFadden, on this interaction between hydrodynamic flow and the binary. So I want to start by pointing something out. And what I'm going to show you here in a second is I'm going to show you some snapshots of numerical simulations of an accretion disk and a binary, and I'm going to order them by what I'm calling Q here, which is the mass ratio of the binary. And so this is just the ratio of the smaller black hole mass to the larger black hole mass, so the mass of the secondary over the mass of the primary. And the binary is on a fixed circular orbit, and we're going to look at what the binary, how it perturbs the accretion flow. So here, if we start with very small mass ratio binaries, so the secondary is of order a millionth or so of the primary's mass, and this is something actually you might find for an Earth-Sun-like system in the early formation of the planets. And what you find here is that this secondary, this is the smaller black hole, causes linear perturbations in the density of the disk. And these linear perturbations propagate outward and are wound up to create spiral density waves. And these spiral density waves then can back react on to the binary and cause what's usually an inward migration, which is important in the study of planets, so-called type 1 migration of low mass planets. So for low mass ratios, linear spiral density waves are perturbed in the accretion flow in the disk. So now if we increase the mass ratio to say 1 to 1,000, this is something you might find in the early solar nebula again for the Jupiter, kind of Jupiter to Sun mass ratio. You find that the perturbations in the density of the disk are now nonlinear, and they shock as they propagate away from the smaller secondary planet or black hole or binary component here. And when they shock, they deposit angular momentum and clear out a low density gap, which is the red here. So white is high density, red is low density. And they clear a gap in the orbit of the smaller binary component.
So you were saying it consists of big black hole, small black hole, and some gas.
Mm-hmm.
How is the gas distributed?
So the gas is distributed initially in these simulations. It's distributed as uniform density and pressure, and we assume an isothermal equation of state. A few of these things have been relaxed, of course, but and then you just have initial Keplerian type velocity distribution, and you allow a steady state to be found. No, in this case, it's purely hydrodynamics plus Newtonian point masses orbiting each other on a circular orbit. And again, these things have been relaxed to look at eccentric binaries and cooling and other things. But for now, just to make this point, this is all all we need. Yeah. So we have very small mass ratio, spiral density waves, and no gap to larger mass ratio and an annular gap in the orbit of the smaller black hole or planet or whatever we want to call it. So if we increase now finally to near equal mass ratios, which is what is important for most of what we expect black holes at the center of galaxies, the large ones, the mass ratios they will have, then we find that there's again a low density cavity region cleared, but it's no longer in a ring in the orbit of the secondary, it's in a large cavity surrounding both black holes. And what's more, you can notice there are some interesting features here where this cavity is no longer symmetric, and more than that, you can't see from this snapshot, but it's time dependent. The solutions seem to transfer from these steady state ring gaps to non-steady state lopsided cavities. And sorry, what was that?
What is causing this sudden spiral, sudden step in the radius?
The radius.
You see this tracks, right? There's a sudden jump in the radius. This is not a graph.
Oh, so this is so this is this number. Yeah.
In the simulations. So I assume these are all tracks.
So this is sorry. I'll explain a little. These are two-dimensional contours of surface density of a gas disk, and so the colors, for example, are high-density spiral density waves and low-density regions in between. Or for here, again, high-density white regions and the red regions are low-density. And so this is two-dimensional spatial plot of density. I mean, does that change that? Okay, yeah, thanks. But the point I want to make with this is that this transition from having no gap to a gap is important, and it's well studied in the planetary literature. It changes the rate at which the planets move in towards their star, and it changes the accretion rate onto the planets, etc. And it depends on the hydrodynamic parameters of the disk. For example, its temperature, which is encoded in the Mach number of the disk here, and the viscous forces in the disk, which is encoded by this alpha parameterization here. So there is a well-defined mass ratio at which this transition occurs, and it depends on the hydrodynamic properties of the disk. However, this transition from gap-opening planets to near equal mass ratio, what we'd usually call black holes, has not been studied about where it occurs or why it occurs, and it's important because it leads to these time-independent solutions, which can lead to well, very far there, which can lead to variable accretion electromagnetic signatures that we'd like to look for in the centers of galaxies. So I just want to talk about now, with some time I have here, what we've been doing to understand why this transition occurs and where. And yeah.
That also assumes that the scale height of the disk is small.
Right, so by the scale height, you can kind of call that the temperature of the disk, how hot it is. A hotter disk will be much more puffed up and have a larger scale height. And at some point, if the scale height is large enough, these gaps will overflow no matter what. So that comes into understanding also how these transitions depend on the hydrodynamic parameters. But for most thin disks, which can cool efficiently, you won't have this overflow just from the thickness, because these are two-dimensional simulations that we're using to probe this problem. So to understand where this transition occurs, I'm going to start with actually just the purely gravitational part of this problem without the hydrodynamics, and that's can be done with the restricted three-body problem, which in the restricted three-body problem tells you how a massless particle moves around the binary, what the orbits of a massless particle are around a binary with some mass ratio and eccentricity, but from now just circular binary. And so that's interesting because we can look at a whole plane of massless particles in the plane of the binary, and that tells us what the gravitational effects are on the disk without pressure or viscosity. We kind of want to start by asking, how do you go from these ring-shaped openings, which have an inner kind of portion and outer kind of portion, just speaking morphologically now, to these cavity-shaped solutions, where the center has been cleared out. And So to do that, we ask, in the restricted three-body problems, how can particles move back and forth across the orbit of the binary? And one thing we use to understand that is that the restricted three-body problem emits a conserved quantity called the Jacobi constant. The important point about this is that it acts like an energy, and we can ask for a given particle with some velocity in the potential of the binary, can it pass over this barrier between over the orbit of the secondary? It's the same as asking if you have a ball with some kinetic energy on a hill, there's enough kinetic energy to pass the hill or not. And so what we do is, as a function of binary mass ratio, we prescribe a velocity distribution, which is, you can do a number of things, but we just allow velocity distribution to be Keplerian far away from the binary, and Keplerian on each of the binary components. And we ask which particles are trapped outside the binary's orbit at all time, and which particles are trapped inside the binary's orbit at all time. And these colorations are blue for trapped outside, red for trapped inside, and green are the particles in the orbit of the binary, which are free to move back and forth. And so if we just stare for a moment at the change in this morphology as we increase from very small mass ratios to larger, to larger, to larger, to larger, to unity mass ratios, you see at first something familiar from the pictures I was showing before, that the size of this inner trapped region decreases, but also this green region increases. And so the question is, what happens to these green particles here? Are they expelled to make something that looks like a gap? And so what we do is integrate the restricted three-body problem for these same initial conditions. If you just imagine these are all test particles, and we integrate the binary, the orbit of each of them, for 100 orbits or so, we find that indeed the coloring holds as it should if you're integrating the problem correctly. And we also find an interesting change here. For the small mass ratios, these green particles mostly stay in the orbit of the secondary. But as you increase the mass ratio, they start to be expelled until here you've passed this transition from here's mass ratio of 0.01 and here's 0.1. And in this case, you have something that looks like the situation of a cleared out region or cavity, versus here, you just barely have particles on orbits in the orbit of the binary. And so actually, we can point out beyond that 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 was after 100 orbits. If you look at just after one orbit, that these green particles actually cleared away in an interesting way through spiral arms, which we see in, well, streams which we see in the hydrodynamical simulations as well. Okay, so I'm not sure how I'm doing on time, so I better speed up here, I think.
8 minutes.
8 minutes, okay. So, yeah, I guess I wanted to come back to some point you see that, well, we'll get there. Okay, so if you notice, there are no longer, like I said, there are no longer orbits in the orbit of the binary after this certain mass ratio, and that comes back to a well-known fact from the restricted three-body problem, that the equilibrium points of the binary potential, there are stable ones, these two right here, called L5 and L4, and they're conditionally stable, only for small mass ratio binaries, less than 0.04. And so that's why you lose those stable orbits. And what's interesting is that we think this has a lot to do with where this transition to the cavity occurs. And so to show that, we've done full hydrodynamical simulations, two-dimensional, with Paul Duffel and Andrew McFadden's code, which is called DISCO. It's a moving mesh code that solves the equations of hydrodynamics. Moving mesh meaning we have rings that move around with the flow, the Keplerian velocity. And so if you want to talk about this numerical code, it's called DISCO. And so what we do is we do simulations tailored to these same mass ratios. And what you find, interestingly, is that this transition to this elongated time-dependent solutions occurs at about the same place so that you lose the stable orbits. And if I want to show you more about what's going on here, in these hydrodynamical simulations, I've tracked the flow of gas across the orbit, because that's what I'm saying is important here, that you can stably move gas across the orbits or you can't. So for these very small mass ratio guys, where you have a small low-density ring cleared, we have red stuff that started inside the orbit and blue stuff that started outside. If we watch how this evolves in time, you see that the gas moves really nicely on what are called horseshoe orbits, which are stable orbits in the plane of the binary. These are these orbits that you can have when the mass ratio is less than 0.04. And so gas can move in stably across the binary's orbit, which is, it must if you have viscosity, which is moving gas inwards. But now let's go above this transition and see what happens. So this is Q.05, just above the transition. And now if we watch what happens to this red material and these large velocity vectors, you see that gas is flung out here from the L4 point. And our thought is that this is what's causing this instability, which creates this lopsidedness in the disk and moves you to the time-independent solutions. If you also notice, if I start this movie over again, there's no longer gas just moving across the secondary. There's also gas moving out of what's called the L3 point, which is another low point in the potential right here. So you generate these double streams, which we also think are important for creating this instability. So in the transition from the low mass ratio transition from spiral density waves to gaps in disk, there's a hydrodynamic dependence on temperature and viscosity. So we also asked, does this transition depend on the hydrodynamics? And so we are continuing these are preliminary results from a parameter study we've done where we've changed the temperature of the disk, which changes pressure forces, and we've also changed the viscous forces in the disk, which can act to overflow gaps and wash out small features. So just quickly then I want to show you the preliminary results from this. So what I'm plotting as a diagnostic here is the amplitude of the variability onto the primary. So you're tracking accretion onto the larger black hole and applying that as a function of mass ratios right across where we think the transition should be. And so for the fiducial viscosity and temperature, which are the snapshots I've been showing you and the simulations I've been showing you, you do find that there is this kind of drastic increase across this region of mass ratio space. There is some, we could talk later about details about what might be going on here, but if we look at this plot for a number of different temperatures, viscosities ranging from 4 times temperature to 1/9 the temperature, so a large range, you find this kind of feature stays the same. And if we look at them all together, it seems like there's this is an important region of mass ratio space, almost not independent, but regardless of what the range of pressures and temperatures are for a thin disk. So I think I'm just going to leave with that for now. And Zoltan's going to talk about how knowing where this transition is important for, yeah.
You're assuming there are no intrinsic springs, right?
No, so these are Newtonian calculations so far. The binary is far enough apart that Newtonian's a pretty good approximation. Mm.
So maybe while
Oh, here, you can watch this while stuff happens.
Dalton is getting ready, if you have any questions for Daniel.
Just quick clarification.
Yes.
Last graph you showed us, you showed the variability amplitude.
Yeah.
Of what?
Oh, so that was accretion onto the primary. And so there are a number of different diagnostics we could talk about for seeing what's this, but that was, what I think that's telling me is when this second stream starts to accrete onto the primary, and this is, I think, has a lot to do with when the transition occurs. So this was just accretion onto the primary, which is measured in a specific way. It's a standard deviation of the accretion rate in time onto the primary, the larger black hole.
So sort of a delta M over the mean? Or?
Yeah, it's literally the standard deviation of a time series of accretion rates. So in a little region, yeah.
So the transition doesn't depend on the separation of the binary?
So in these simulations, the separation of binary actually scales out of the equations because it's Newtonian and because the disk is isothermal. So you could rescale that to any mass of the binary and any separation you want. When you add other physics, you would have to specify that.
Maybe a follow-up.
Yeah.
Could you express then the separation in terms of m and make it scale free?
Yeah.
What is the separation of these things?
Oh, so these would be sub-parsec separations. I usually have in mind thousands of short radii. So it has to fit inside of a gas disk, and then the gas disk becomes stable at some certain unstable size, and you can put some criteria on separation from those kinds of arguments.
But I mean, in some ways you have the period and the sound speed. Because if you have a very high sound speed, the gas disk would feel much faster than an orbital period.
Let's see, but I'm just, in these simulations, we're alone the mass and the separation scale out, so there's no well-defined period.
But your mag number is basically in relation with the orbital period.
That's true. Yeah,
So that's
true.
what would scale.
Right. That's it.
Okay, so we now have Sultan. Since it's informal, I won't say your last name.
Yeah, thank you. So, first of all, thanks for the invitation. It's great to be here. And now that you know everything about the theory of accretion disks around binaries, I want to ask how we might use this behavior to actually find binary black holes in the real universe. I should say we're in a special time because over the last several months, there are actually several surveys which started looking for binary black holes using this variability. So, and the people involved in this work besides Dan are another student, Paul Duffel, who moved to Berkeley from NYU, and my faculty colleague at NYU, Andrew McFadden, who wrote this code that we're using. So let me just spend 1 or 2 minutes on the general motivation, which is actually really simple. The logic here is very simple. We know there are supermassive black holes in galactic nuclei. We also know galaxies merge frequently, several times over their lifetime in the age of the universe. And so we expect supermassive black holes to pair up frequently in galactic nuclei. And we also think, although this can be debated on the discussion session, that they spend a long time, fair fraction of the age of the universe, before the black holes actually coalesce. So therefore, we actually expect binaries should be commonly found in galactic nuclei. Now we also think gas is delivered in the mergers of galaxies. Oh, sorry.
You don't want to be the
Can you hear me in the back?
It's for the recording.
Ah, okay.
More like the other way around. Just turn it like that.
All right. Like this?
Yeah.
This feels weird. Okay. How do I look? Okay, so we also think the galaxy mergers deliver gas to the nuclei at the same time. These black holes are trying to coalesce, which can make them bright and gives us hope we can find them in electromagnetic surveys. Now, despite this fact, as you probably all know, that there isn't a lot of binary black holes out there that we know exist. There are a few candidates. And so the reason most naturally for this is that the black holes do quickly move from large separations to small separations where they're undetectable as resolved binaries. So the only way to detect them at galactic nuclei when they form a bound pair is through some kind of indirect signatures. So, and the general theme of this search, I think, overall, is that any emission that is produced by this pair of black holes around the time of the merger, just before and during and after, is going to be time variable. So that's also good news because there are lots of time variable surveys coming up of the sky. So we can look for those. Now, in particular, I will go back to Dan's talk and talk about how you might look for periodic variability based on what we're finding in the simulations. But I should just make one more general point. You can look for binary black holes through electromagnetic surveys of the sky which have time domain data, or you can look for them in gravitation waves by ELISA or by pulsar timing arrays, where you try to discover them through gravitational wave emission, and then you try to confirm them with electromagnetic signals. So just another cartoon picture in terms of pedagogical introduction. We do have a standard picture of a quasar, how it operates, through an accretion disk around the supermassive black hole. And now if we have a second black hole, which is placed there by the galaxy merger, the most obvious thing you can do as a theorist is to just take this accretion disk, which is, again, I said is reasonably well understood, put a second black hole here, and just ask what happens. That's what Dan talked about. It's an accretion disk around 2 point masses. Now, there are 3 reasons you care about this very simple toy problem. Well, first, actually, the fourth one is it's a nicely well-defined physics problem. But the 3 practical reasons is the orbital decay. So there is the disk enveloping the 2 black holes, and it will make the 2 black holes merge because the disk becomes not axisymmetric, as you've seen in Dan's talk. And so there will be torques which drive the black holes together. And you really care, if you want to find the black holes, how long it takes for the black holes to move at each radii, because that determines how many black holes there will be on the sky at a particular orbital separation. Now, of course, we also care about directly how much gas is falling onto the black holes. Is there gas near, within few Schwarzschild radii of each of the both black holes, so that they can produce bright emission? And how does this black hole accretion actually happens on small scales? This, of course, affects the basic thing, the spectrum and the time light curves of these objects, the basic observability. And then a third reason you care about this, in principle, is if you look for these objects through gravitational waves, either through LISA or pulsar timing arrays, and if there is lots of gas around the black holes, you do care whether the gas might actually deform the waveforms, the gravitational waveforms, sufficiently that you should worry about this. So I'll try to make one comment about that at the end if I have time. Now, just a quick thing about the first problem, the orbital decay. As I said, this is very uncertain. I think the only thing that's generally believed is that the orbital decay is generally slow. So what I've shown here in this plot, it's a bit busy, but it's actually a simple plot. This is the frequency of a black hole binary of equal mass. This is the orbital period in years. So this here is 10 years, this is 1 year, this is 10 to the 8 years, and this is 10 minus 5 years, which is, I guess, minutes. And then this, in the y-axis, is how long a binary spends at that particular orbital separation based on cartoon models that we have at the moment. And so these are for different mass black holes. And the binary, of course, comes from large separations, long orbital times, and moves this way as it's approaching, as the binary is approaching coalescence. And there are 3 regions where you can see that the lifetime changes. So this here is the time spent at that particular separation in units of 10 to the 7 years. The reason I chose that unit is because that's the typical lifetime of a quasar. I'll come back to that as well. But so 1 here would be you spend about 10 million years, so that's as long as the lifetime of a quasar. That means we roughly would expect, therefore, as many black hole binaries as quasars at that particular orbital separation. So this coming from the large separations, the first process which moves them together is stellar scattering. The black holes are surrounded by stellar bulges and scatter stars, and this process slows down as the black holes move inward. So let's look at the 10 to the 7 solar mass black hole pair. So that's this one. Then it starts to move increasingly rapidly together, and that's due to interaction with the gas disk. And I won't go into any of the details of this. I guess we can in the discussion. Again, this is poorly understood. In fact, there's no self-consistent calculation of the migration, including the torques through the disk from large radii. So these are toy models. And then finally, at the last stages, gravitational waves take over, and that's the third process, which finishes the merger. Gravitational wave emission reduces the energy and angular momentum of the binary and makes them merge. So that's what we have at the moment. I should emphasize, since this talk is about observations, is that we care about orbital times of maybe a few years down to few hours. So this green shaded region. Because we can't really look for 20-year period binaries. We don't have 200 years of data. And we have to integrate with the telescopes for reasonable time, so we can't look for extremely rapid periods. So in electromagnetic surveys, you would be looking for here. These would be the gravitational wave frequencies of the pulsar timing arrays, and the very last stages would be caught by LISA. So I'm going to come back to this in a second. Let me now go to the variability. So referring back to Dan's talk, and again, just in this talk I want to be motivated by looking for electromagnetic emission. So looking for binaries in this orbital separation, which is before the gravity wave takeover. So we're not actually talking about the last bit of the merger. We're trying to catch these binaries at slightly larger separations, when I think these hydro simulations are quite relevant. And so in Dan's talk, you've seen that if the mass ratio of the binary is about 1 to 20 or more equal, then the accretion on the binaries becomes variable. And in fact, the other features that happen about this transition, the gap, annular gap in the accretion disk, it becomes more like a central cavity. The disk becomes lopsided, and also the binary probably becomes more eccentric because of the lopsidedness of the disk. But here I want to focus on the variability, which we expect to be present. Now, I should emphasize that in merger, if you go back to, if I put on my cosmologist hat and I try to model the mergers of black holes, most people expect that the mass ratios are quite equal, because very unequal mass unequal mass galaxies never actually finish the merger, because that dynamical friction takes too long, and tidal forces can disrupt the smaller galaxy falling in. So in general, we expect maybe in this 1% to unity mass ratios. So we do expect them to be in this regime where they're variable, and that's good news. Now the first question you should ask, dense simulations were only hydrodynamics. So do we actually expect the photons to be doing something similar than the gas accretion rate? So in this particular paper, we've augmented the simulations with a treatment of heating and cooling. So we can actually follow not just the hydrodynamics, but also the thermal state of the disk. I won't go into details, but it's basically solving the energy equation explicitly. So this, for example, is the snapshot of a disk, just like Dan showed. This is the surface density, gas surface density. And this here is the corresponding surface luminosity, just sigma t to the fourth blackbody emission from the surface of this disk. And you can see that there's very hot rim of this cavity. There's hot regions in the disk. And there are shocks which happen inside, which create hotter regions. And overall, this disk is actually very bright. In fact, if you ask how bright it is compared to just having a single black hole, it can be even brighter. It's not actually any dimmer for sure. Now you can, again, going to more general mode, you can therefore hope to find in observational data a whole bunch of things that you might look for. One is periodic variability. So the emission from these mini disks, we call these little disks here mini disks. This emission, if the streams keep shutting off and restarting, they're like, I call them phoenix disks, because they die and reborn periodically. This happens as long as the viscous time, the drainage time of the disks is shorter than the orbital period of the binary, so that they can die and reborn again. You can also expect periodic variability even irrespective of hydrodynamics, just because the binary is moving, and you have Doppler shifting of even the continuum emission. If the binary is closed, this is relativistic, and there's also Doppler shift in the frequencies. The hotspots that you see here can produce characteristic spectra, so they can be harder than a usual quasar, and maybe in the UV or X-rays they show up. When these accretion streams hit the these accretion streams, which are moving at high speeds inside and hit these mini-disks or hit the edge of the cavity, these shocks are very bright. Because we have actually a very bright UV source, this actually contraries to some previous expectations. But I think you might actually look for broad lines which are stronger than in normal quasars, just because the broad lines in quasars we think are produced by the ionizing radiation, UV radiation from the inner region of the accretion disk, which is ionizing gas further out. Here you might actually have broader lines which are stronger, and of course they might periodically vary if this UV power source is periodically varying. And then if you're optimistic and you think you can probe the very inside of the disk in the iron K alpha line, that should also have very different spectral shape than for a normal single black hole accretion disk, just because the morphology of the gas is so different. So how many minutes actually? I have 10 more, okay. So I think the first good news is that this luminosity, if you actually take this picture here and you plot up a spectrum as a function of time, you do find encouraging signs. So this is essentially the same kind of picture. The left panel here shows the accretion rate in black. So this here is time on the top panel, 2,200 orbits to 2,300 orbits. So this is over 100 orbits. The black is the mass accretion rate onto the two black holes summed up. And the red is the luminosity, total luminosity coming out of this accretion disk, summing up the black body emission from the surface. And you can see that they track each other pretty well. The bottom is a Lomb-Scargo periodogram, and both show big spikes. I'll come back to these spikes in a minute, but they're characteristic periodicities in these light curves. I should also say that the spectrum also shows this variability more strongly on the higher frequencies and the lower frequencies. So this here is the spectrum. The top is the total spectrum at 2 different times. Black and red are 2 different times. And this is composed of 3 different contributions. This is the outer disk, which dominates at low frequencies. The very hot region of the spectrum is actually produced by the mini disks, which are very bright, can actually be quite bright compared to, you get to tap the orbital binding energy of the black hole as it shrinks. So this can actually make the mini disk much brighter than a single black hole disk. And then the streams.
Your predictions for that kind of stuff.
Sorry?
Your predictions are that the luminosity will be the order 2 to 4 times larger than a single black hole.
It can be even more actually. For again, the reason I can't really answer this because it's not a self-consistent calculation. It's a snapshot where we do a 10,000 orbits. And it is true in this calculation that the strongs are very very strong. You expect, and you can actually extract the binding energy of the black hole. But if you do that too strongly, you of course start driving the binary too fast, and the process should stop being. It's not self-consistent anymore. So it could. Well, I don't know the answer actually to this. I just think in principle it could be quite a lot brighter for some time at least. It could be a transient state. I think the bigger conclusion is there's no particular reason for this to be dimmer than a normal quasar. I think that's a fair statement. Okay, so let me go back. So now, if this object is producing periodic variability, and I already told you that these objects are not necessarily rare because I explained this plot already. So for example, if you look at 10 to the 7 solar mass black holes, at orbital periods of few years, they live there for as long as a quasar. So if you assume that every single quasar in the universe has to do with the mergers of 2 black holes, then in fact you would conclude that a large fraction of quasars are binaries. At least the ones which are 10 to the 7 solar mass black holes. So it's actually, because of this, I'm not going to explain this plot. I think it's a little too complicated. I just want to maybe I'll skip it and just say here, we made a prediction in this paper that people should look in large optical surveys and look for periodically variable quasars as possible candidates for binaries. And you can, of course, from this, you can actually predict, for example, the bigger black holes, 10 to the 9 solar mass, they're the brightest quasars. They are easier to find because they're brighter, but there are fewer of them. So you can calculate the number density, and for example here at 1 year period, you can see that they spend much shorter time than a 10 to the 7 solar mass black hole, 2 or 3 orders of magnitude less. So for example, you can make predictions like this. There should be a lot, in a wide survey, in a bright quasars, it should be less common to find binaries than in the dimmer quasars. And well, I should at least say that when we made this statement in 2009, there weren't really time domain data. So there was the Sloan survey, which had a little bit of time variable data. And in this plot, we just, again, sorry, I'm not explaining this, it would take too long. The only point I want you to take out of this plot is that this is the area you should cover, so in square degrees, and this is the magnitude in the I band. If you make some reasonable assumptions, I think, about how bright these objects are, this is the kind of survey you need to find a bunch of order 100 periodic sources. And so Sloan was just below. There was a deep Subaru survey, which is just below. But there's LSST here, which is a very large survey. Will cover half the sky to a very big, very large depth. So you should find gazillions of these periodic sources in principle. And more interestingly, there's the survey, which is called the Catalina Sky Survey, which earlier this year essentially performed this exercise. And there are other surveys, PenSTARS, which have done it in the meantime. And actually, we ourselves are working on a similar analysis with another survey. But here is I think, I know we're supposed to be pedagogical and not talk about recent results. But this was quite exciting. So this object here, called PG1302, was published in January, or February maybe. This was pulled out of a sample of 250,000 quasars in the optical, in this survey called the Catalina Sky Survey. And this here is the light curve of this object in the V band. And this here is 10 years. This is days. This is in days in the bottom. And this is in magnitude. So you can see there's a plus or minus 15% variability. These blue and black points are span about almost 20 years of data. And there's actually data going back even longer, a few previous observations, because this is a very bright, one of the brightest quasars on the sky. So it's actually got data back. In fact, it has data back here 100 years in the CFA plates, optical plates. So this object is a redshift 0.3. It's a very bright quasar of order 10 to the 9 solar mass black hole. And this period is about 5 years, observed period. So the rest frame period of this object would be then, of this variability is 4 years. It's because it's at redshift 0.3. So that's great. We can declare victory. Of course, you want to go a little further and prove things, because there are other things. Well, there's even statistical issues which could be part of the discussion. Is this object real, given that it was found among so many? Or it could just be noise. But let me try to interpret this based on what I was just saying. So first of all, I think one important question is how you prove that this periodicity is from a binary, and what is the actual orbital separation of the binary. So the first important point, again going back to Dan's simulation, which he didn't actually get to tell you, but the periodicity of this mass accretion or luminosity variation strongly depends on the mass ratio. So here are two of our simulations, and this actually is confirmed by other groups. So I don't think this is, this I think is relatively robust in general, this result. So mu equal mass is a 0.5 binary with mass ratio of 0.5, 0.1 in the bottom, 1 to 10. And this is the periodogram of the mass accretion rate. And in the bottom you see that the spike, I don't know if you can read this, the axis is the frequency. It's not showing up very well on the screen. So there's a spike at the orbital period. So this stream is shutting off and restarting at the orbital period. And you should see that in the data as the optical variability. Here, for the more equal mass binary, this large spike is actually at 5 times, roughly 5 times longer period. And that's because the strongest variation is not at the orbital period of the binary. It's actually orbital period of the gas out here at the edge of this cavity. This cavity is very lopsided. It's not axisymmetric. There are hot and dense spots along the rim and less dense and less hot spots. So the periodic variation is reflecting the orbit here. That's actually very interesting. I should say this ratio, the size of this cavity and this ratio of the period, the largest period to the binary period, does depend on these parameters, viscosity and temperature of the disk. Now, you can ask, okay, that's interesting. If this is a mu equal mass binary, 2 minutes left. Okay. Maybe I'm gonna 2 minutes. So maybe I just say in words. This is a very important question because the observed period of the binary is 5 years, and that's the optical period. If this is near equal mass binary, then the true period would be 0.7 years. And that would be actually a very dramatic difference in terms of this object would then be in the gravity wave driven regime as opposed to the gas disk driven regime. It would also be much rarer because the lifetime, as I showed in that plot, is very steep function. This is almost the cube of the time. Whoops. The residence time here in the gravity wave driven regime is go like the orbital time to the -8/3, very steep. So if you make the orbital period 5 times shorter, you expect 100 times fewer objects. So that's very important. And one way, maybe I will skip this as well. We can try to confirm this from the data, which is the case by looking for the additional peaks. So we actually, I think that's a general pedagogical message. You can look at periodogram and try to find multiple peaks, which should be there, which we actually didn't find in the data. Okay, the last point, since I have only 1 minute left, which I do have to emphasize, because there's another explanation which is confirmable for this object, which is that the periodicity in the optical has nothing to do with hydrodynamics, but simply relativistic modulation of the luminosity due to the orbital speed, which varies across the orbit, the line of sight velocity. So, so this is the cartoon picture. Another thing I didn't say in the simulation, most of the accretion is actually on the secondary. So we expect the secondary to be bright. It's going around the primary, and the line of sight velocity is sinusoidally varying. And if you simply evaluate, I won't go through the equations. If you simply evaluate the periodic variability you get from this, you find that if the black hole is massive, 10 to the 9 solar mass or higher, the mass ratio is quite low, so that the secondary moves fast, and the disk is not too tilted, then the entire 15% variability can be just caused by this kinematic effect, and for completely reasonable parameters. And then the last point I want to make, and then I can stop, is that there's a way to confirm this hypothesis, because this relativistic modulation is, well, maybe I'll skip that. Sorry. So the relativistic modulation is mostly coming from the fact that the spectrum is not flat. You have a spectrum which is steep as a function of frequency and is modulated like this, and you're measuring the flux in the V band at a particular frequency, so the flux is varying over time. If you go over to another band in the UV, where the slope is even steeper, you expect a different, you expect the variation to be very similar, but have an amplitude which depends on the spectral slope. So we simply looked at this object, looked back at archival data. It turns out this object has archival data in the UV back to 92. And we plotted the UV points. And we basically found that they do track the optical points, which are the black here. The blue and the red are UV points in 2 different UV bands. And you can see that they actually follow the same variation, but scale up by exactly the expected ratio of the spectral slopes. So we actually claiming in this last paper that this is a good hypothesis for the variability of this particular object. Could of course be confirmed in the future with more pairs of UV and optical and infrared data. So I think I won't talk about the gravitational waves. I can answer if people ask, but I should just stop because Enrico is looking menacing.
What about gravitational waves?
Thank you. Am I allowed to say one thing? So I think actually this can be very quick because the answer is on this slide. I really only have one slide. I can do it in one slide. So basically there has been quite a bit of work about this, of course, and I think the answer is almost always no. The gas has no effect. The gravitational waves can affect in principle the waveform by affecting the orbit of the binary through various effects: hydrodynamical drag, actual drag force, the black hole is accreting from the accretion disk and absorbing the angular momentum. Or they can be migrating due to the global torque exerted by the disks. And I think the answer is always that there's not enough gas to modify the waveform for LISA or the pulsar timing, with one exception, which might be a little niche regime actually, which is when the so-called type 2 migration happens. So that's when there's a very unequal mass binary. So this would have to be a unusually unequal mass, 10 to the minus 3 mass ratio, supermassive black hole and a intermediate mass black hole. And in that case, actually I was involved in this work as well, we said that this is like type 2 migration of planets. So that's Dan's picture with a gap. The planet or the secondary black hole is moving with the disk on the viscous time, which we said could speed up the evolution and modify the waveforms by roughly 1%, in the sense that 1% fewer orbits would be spent in the LISA band at a particular frequency. But the interesting new result we got, and that's the main result I wanted to show, is actually it's the opposite. So you actually we did a simulation of this regime where here's the secondary, this is the accretion disk, and this is different from what Dan showed in the sense that we took the secondary and by hand forced it to migrate inward throughout the simulation time. And that's basically like gravitational waves pushing the binary inward. And then we can just then measure the torques exerted by the disk back onto the secondary. The disk gets distorted. And what we find is the disk is actually pushing the secondary outward as opposed to inward. So if you didn't push the secondary, this would settle into a steady state where the secondary is swept in with the gas, and the gas effect is inward. But when you try to push the secondary, we find the gas actually resists and pushes outward, roughly by the same magnitude, 1%. And I think that's, again, it's a niche topic, I think, because it's LISA far in the future, and this particular MRIs. But I think gas is important in that regime, potentially.
There's been a letter a few months ago, I found very interesting, where they show that the impact of dark matter between the primary and the secondary body can affect the waveform in a measurable way. I think it's Fisher method, so it's not a full Monte Carlo study, but if the object is massive enough, then you can inside a cluster or something.
I think the density of dark
Yeah.
matter.
You just read the paper. I mean, it's PLA, so I guess someone checked it. Yeah, I can point it.
Given the binary separation, then I'm just curious what binary separation that's important.
So in this case, you have luminosity, so you can have an m dot, and you can basically calculate the density and temperatures that you expect, and see whether or not the cooling time is efficient, and whether or not you can actually thermalize. But this goes to the question, you can also calculate whether or not the Mach number or the temperature is comparable to the overall shear in this particular case based on your solution.
Right, so I think we're just making the first steps, and we haven't here. This is a calculation where it's assumed thermalized instantly, basically. So we do have heating and cooling, and it's not assumed to be in equilibrium. But
But you know the cooling function.
yes,
You know m dot.
right, we could do that.
And then you can see whether or not the Mach number is in the regime in which you actually have a gap. But maybe that tells you that the variability is either driven by the disk.
The very fact that you're modeling thin disks means that Mach number has to be lower than
I think the big question is, does the disk actually puff up and heat it and puff up and becomes a thick disk? And then the other important thing which is missing is, which we're just putting in, is radiation pressure. So depending on how you scale this system, if it's close in, radiation pressure actually can become important.
How close to the edge of the
Actually, it depends on which param. I should show you a plot.
Okay, well, let's thank Sultan and Dan again.
Thank you.
For next speaker.
it's not allowed.
Eh?
So it's not allowed to solve.
Yes.
Only if you really have the right solution you can
You're
speak.
not allowed to solve problems. So.
No.
Oh yeah. You just plug
can
this
connect it for
in.
you.
The laptop doesn't fall asleep.
I can connect it. Why don't you put the microphone? Thank you.
Yeah, it's 45. Yeah, after 35. And it's me. Well, I would like to start by thanking the organizers for inviting me to what I'm sure will be yet another exciting AstroGear meeting in this very exciting city. I actually wanted to talk to you today about a particular question, and that is a problem of missing red giants in the galactic center. So I'd like first to discuss why is this a problem to begin with, or a puzzle, and then towards the end tell you a little bit about the work that my student Forrest Kiefer and I have been doing related to this problem. Milky Way today